Hello, everyone. Welcome to Tim's Defense. Tim started working with me from 2016, and first he got a master's degree, and then he entered into the Ph.D. program. His research is focused on pulse-coupled oscillators, and in the first, I think, several years, it was mainly using kind of control theoretic approach to analyze pulse-coupled oscillators as well as its applications. And in the later part of his research, he basically focused on reinforcement learning-based approach to address these kind of systems. Okay, so yeah, I mean, today he will give his defense and PhD defense and Tim. So whenever you're ready.
All right, thank you, Dr. Wang. Again, just introduce myself, I'm Tim Angel, and this is my dissertation defense on my dissertation on pulse-coupled oscillator networks, achieving phase continuity and learning optimal control in physical systems. Let me give a brief overview of kind of what my talk is going to be on. I'll introduce what pulse-coupled oscillators are for those of you who aren't very familiar with them, as well as go over some preliminary details about pulse-coupled oscillator networks. I'll then go into talking about achieving phase continuity in pulse-coupled oscillator networks and the methods that we have for doing that, and then looking at how we can achieve synchronization and desynchronization in networks where we have this sort of phase continuity. I'll then transition into talking about finding an optimal phase response when I use reinforcement learning techniques to determine that, which after that will then follow up with any conclusions as to work. At that point. After that point, you'll be able to ask any questions you guys have. If you have questions, you can ask them live. You can unmute yourself, or you can just put them in the chat and we'll try to relay them in that way. So let's begin by looking at what a pulse-coupled oscillator and a pulse-coupled oscillator network is. So pulse-coupled oscillators have their inspiration in biology, in the natural organization that various biological systems have. It was first studied by a man named Charles Peskin in cardiac cells or pacemaker cells of the heart, but it's also studied in fireflies, neurons, as well as audience applause. So for example, in the animation you see there, you have a bunch of fireflies that are all flashing randomly, but by making small adjustments to when they all flash, they're able to achieve this synchronization where they all begin to flash in sync with each other. Just by looking at and perceiving the natural responses and flashes of their nearby neighbors. What is the mathematical model for this? So we have a bunch of nodes in a network where each node is an oscillator. Basically, an oscillator is something that's fixed. They have a phase variable, which I'll denote by phi, which is increasing at some frequency omega. When it reaches a threshold value, then it resets back to 0 and it continues on. So you can think of the phase variable as those circles that are all moving around the outside of a larger circle. Whenever a oscillator reaches a threshold, which is up at the top, it then fires a pulse, and all of the oscillators that are connected to it in the network will receive that pulse. Based on how you choose to respond to those pulses, you can get various different behaviors, such as synchronization, where all the phase values line up together, or desynchronization, where all the phase values spread apart. And so you have lots of different applications for these pulse-coupled oscillators, not only in just modeling different biological systems, but engineers and scientists have used these in wireless sensor networks and being able to synchronize the timing between what they recognize as a common value of time among various remote sensors, as well as being able to schedule communication in a sort of decentralized round-robin sort of way without having to have any sort of centralized controller. There's also been studies done in achieving coordination among different robotic vehicles, being able to align or de-align headings for robotics. There's a lot of benefits for using these pulse-coupled oscillator networks, primarily that you have a decentralized communication structure. There's no central node that's commanding everyone else what to do. Everyone's kind of working together to figure out the behavior, but you have a very simple, energy efficient, and robust sort of protocol for being able to achieve this sort of behavior of synchronization or desynchronization. So let's talk a little bit about some of the mathematical preliminaries of what a pulse-coupled oscillator network entails. So you have the oscillator value phi, which goes from 0 up to some threshold value c for each of the oscillators. That phase threshold varies depending on what you look at in the literature. It could just be 1, it could be 2 pi, but really it could just be whatever you need it to be. And each oscillator has its own individual frequency that adjusts its phase value up to the threshold value until it resets. Sometimes the oscillators have a fundamental frequency that they all share, but sometimes it's just each oscillator has its own individual frequency. When an oscillator receives a pulse from a neighboring oscillator, it makes some adjustment to its phase. I'll call that psi. And this is based off of some phase response function that is defined for the oscillator that tells it how much to adjust its phase value when a pulse is received. Sometimes you also see this called a phase response curve or a PRC, so I'll use those kind of interchangeably. If I want to achieve synchronization, there's lots of different strategies that are available, lots of different phase response functions that can be used. One is shown over in figure 2.2, where when it's in the first half of the cycle, it moves backwards, whereas when it's in the second half of the cycle, it moves forward. So this is what's called a delay advanced phase response function. Often you'll have some sort of coupling strength parameter alpha, which will denote like how much of the phase response function value f to actually move when it receives a pulse. There may also be a refractory period during the initial part of the cycle where an oscillator won't respond to any pulses, it won't make any adjustments. But if I want to quantify how well this network is able to synchronize, I can look at a quantity called the containing arc, which is denoted by lambda. Basically, it looks at all the different differences between the phase values in the networks using a set of functions v. That denotes what the difference in phase is between any two oscillators in the network. And then the containing arc is basically based on whatever the largest difference is. So in the figure in the bottom right, that red oscillator and that yellow oscillator on the right and left are the farthest apart. So those are what define the containing arc, the arc that contains all of the oscillator phase values all at once, but that's the one that's the smallest. So I can quantify what that is. Whenever the containing arc gets to 0, all the oscillator phase values are basically the same. So we would say it's synchronized. Alternatively, if I want to achieve desynchronization, I'm going to need a different phase response function. One where in the initial part, I might need to adjust forward in order to move away from anyone that's just fired a pulse. Whereas in the later parts of the cycle, I need to move backwards in order to actually move away. That will allow the network to desynchronize, so everyone spreads apart. In this case, I might have two different coupling strengths, one for that initial part, L1, one for the second part, L2. And I'll need a different measure for being able to know whether or not we've desynchronized. I use the same function z that denote the differences between oscillator phase values, but instead of our containing arc, I'll use this desynchronization measure, which we denote with p, which is just the sum of the absolute value of differences between those v functions and what I would expect the desynchronization difference to be. It's going to be all n oscillators in the network are going to separate out. And so when that desynchronization measure is 0, that means that all the net oscillators have desynchronized. They're all spread out as much as possible. A couple more preliminary definitions that I'll just need to define just so that are clear what we're talking about. For our network, we can define it using a graph that has a set of vertices, which will be just our oscillators, and a set of edges, which note whether or not an oscillator is able to communicate between each other. So an edge denotes that oscillator I can send a pulse to oscillator J. Our graph is bidirectional if oscillator I and oscillator J can both send pulses back and forth between each other. A directed path is just a set of edges that go from one oscillator to the next within the graph. And we say that our graph is strongly connected if I can find a directed path between any pair of vertices or oscillators. So I can go from one oscillator to the next oscillator in the network just by following these edges. Additionally, we can define the out degree and the in degree of a vertex, which is just the number of edges that either leave that vertex or come into that vertex. So the out degree is just saying, here's how many other oscillators this oscillator can send a pulse to. The in degree says, here's how many other oscillators that this oscillator receives pulses from. We can also define the out degree of a graph as just the minimum value for any of the vertices. So with all those preliminaries out of the way, let's talk about the phase continuity method itself. Because when you look at the pulse-coupled oscillator algorithms, they all require that you have an instantaneous change in the oscillator phase variable. So when an oscillator receives a pulse, it makes an instantaneous change to whatever its phase value is. But sometimes you actually need the phase values to change continuously or slowly, rather than changing all at once. For example, to practically implement this into a physical system, if I'm associating the oscillator phase with some robot heading, the robot can't change its phase, can't change its direction instantaneously. It has to take some time. So that kind of implies that the oscillator phase value must also change over time. But also in different computer networks or wireless sensor networks where you're keeping track of time using pulse-coupled oscillators, if you do an instantaneous change in time, you might skip over a process that's been scheduled to occur at a certain time interval. If you skip over that, then that process is never executed, or sometimes if you skip back in time in order to synchronize, then that process may occur twice, which can result in errors and bugs in your code. So often we want the phase value to change smoothly or continuously. So how do we do this? Well, it's pretty simple. You just have to adjust the frequency of the oscillator by some amount. I'll call it omega A. And it needs to adjust by that amount for some finite amount of time. I'll call it out. So as the oscillator changes, it increases its frequency or changes its frequency for that amount of time. Then it just returns back to whatever its initial frequency was. So there's two different ways that we can achieve this. One is what I'll call the constant frequency method, where I keep the amount that the oscillator is going to adjust its frequency by constant. And then I just determine, okay, here's how much time it needs to adjust by that amount in order to achieve the desired phase adjustment psi. Alternatively, I could keep the amount of time that it takes to change its phase constant, and then determine here's how much frequency I'll need to adjust by in order to achieve the desired amount of phase adjustment psi. So I have the constant frequency method, constant time method. There are additional methods that could be considered, but it's important to note that the instantaneous phase change is really just a special case of either of these methods. So what does using these phase continuity methods mean? Well, for a single oscillator, basically, it adjusts frequency for some amount of time when it receives a pulse, and then it returns back. So that's basically the behavior for a single oscillator. But what's important to look at is what happens when the next pulse is received. There's two cases that could happen. The first is that the next pulse that the oscillator receives happens after the oscillator has finished its phase adjustment, its frequency adjustment for that amount of time. In which case, then the oscillator has done its phase adjustment that it's expected to do. It's returned back to its frequency, a natural frequency. And so in that case, there really is no effective change in the behavior of the oscillator. It's exactly the same as if the oscillator had adjusted its frequency by psi instantaneously and just had evolved normally after that point. However, if another pulse is received before the oscillator has finished its phase adjustment, so if a pulse occurs before tau I had finished up, in that case, then the oscillator's only finished a portion of the phase adjustment. It's basically done some fraction of that amount, which we can quantify with the ratio T0 over tau sub I. Basically, this is equivalent to having the oscillator make that smaller adjustment instantaneously and then evolving normally for the duration of the time between those two pulses. So with these two cases in mind, we can basically summarize and model both of these cases together as a potentially time-varying reduction in the coupling strength parameter, whether that's alpha for the synchronization case or L1 and L2 in that desynchronization case. Basically, we have an effective coupling strength that's bounded by 0 at the bottom, that's the smallest key, and whatever the set coupling strength value was. So it's time varying, but bounded in between those in that region. So this will lead us to be able to analyze pulse coupled oscillator networks that have some sort of time varying yet bounded coupling strength. And this is a unique approach in the literature. You don't see this kind of approach in analysis happen, but by analyzing a standard network with a time varying coupling strength, we can associate that with our receiving phase continuity, where the oscillator phase values are changing continuously. Let me give another example for why we would need this sort of phase continuity, specifically within robotic heading. So if I have a set of robots that I would like to control the headings of, whether I want them to synchronize or I want them to desynchronize, robot headings can evolve on an interval between 0 and 2 pi radians, which is very similar for our oscillator phases. So I can associate an oscillator phase with a robot heading. So for each robot, I'll assign it an oscillator, where the initial phase of the oscillator is just whatever the initial direction the robot was facing. And I'll have the oscillator increase at some fundamental frequency. I'll call it omega 0. So if I want to control the robot headings then in this network, I can just assign that the change in the robot heading value is going to be whatever the change in the frequency of the oscillator is compared to its fundamental frequency. Whenever the oscillator has to change its frequency when it receives a pulse, then the robot is going to change its way. However, with robots, as is probably intuitively clear, there's some maximum rotation rate that the robots have. There's this kind of implied constraint. The robot can't change its heading instantaneously. It has to do so over some amount of time at some rate. This implies that there's going to be some constraint on the oscillator phase value. The oscillator can't change its frequency by too much. So I can achieve this using our phase continuity methods. So for example, with the constant frequency method, if I just set the oscillator phase value to never change more than whatever the maximum rotation rate is, then we should be good. We can satisfy that constraint, but that leads into having to deal with these phase continuity methods. So with the robotic heading, whenever the oscillator phase values reach the desired state, then my robot headings will also achieve the same state. If the oscillator phase is synchronized, the heading values will also synchronize, given that control that it's following the adjustments of the oscillator phase values. So if I want to show that my robots will be able to synchronize or desynchronize, all I really need to do is show that the oscillator phase values will synchronize or desynchronize, and they can just follow that robotic heading control algorithm, and that will they will achieve the same state as well. So let's talk about how we actually can achieve synchronization and desynchronization in pulse coupled oscillator networks using phase continuity. So we're going to take the approach of analyzing our network of a standard network, but with a time varying coupling strength. That's the approach that we're taking. And what's important to note is that I don't really care what the value of the coupling strength is in between pulse firings. I only really need to know what the value of the coupling strength is when a pulse is fired and when the pulse is received. The behavior of the network is independent of whatever the coupling strength is in between those pulse firings. So they can be whatever. But that's kind of an important thing to note. So that's what proposition 1 states. And so for synchronization, we're going to look at using the synchronization PRF that's shown in figure 2.2, that standard delay advanced phase response function, where the oscillator adjusts backwards when they're in the first half of the cycle, and when they adjust forward when they're in the second half of the cycle. So we can look at how we can achieve synchronization in a standard pulse coupled oscillator network where the phase adjustments happen instantaneously, but they have some sort of time varying coupling strength function. So we're going to have a delay advanced phase response function that we'll use. We'll need to make sure that all the oscillator phase values are within half of the cycle. So they start out well on one side of the circle, if you will. And then the coupling strength alpha for synchronization just can't converge to 0 at all those firing instances. If it doesn't converge to 0, then we can show that the synchronization of the oscillators will occur. Let me kind of sketch out what the proof is for this. It's pretty straightforward. In the figure shown on the left, oscillator J is the yellow one that's kind of at the back of the pack. At some point, oscillator J is going to receive a pulse because the network is strongly connected. One of the other oscillators will send a pulse to oscillator J, in which case then, because oscillator J is in the second half of the cycle, it will make an adjustment forward, which will decrease the overall containing arc. Similarly, oscillator I, which is the oscillator up at the front of the pack, when it receives a pulse from one of the other oscillators, it'll be in the first half of the cycle on the right side, in which case it will make an adjustment backwards if it's not in that refractory period. Either way, ultimately, for each cycle, the containing arc is going to decrease by some amount. So since the containing arc is always decreasing and won't ever get below 0, it's going to converge to that 0 value, which tells us that the network is synchronized. That's the basic essence of the proof for how that's going to work. So with that in place, we can then talk about kind of extend that result to achieving synchronization with this sort of phase continuity, because we can model this idea of phase continuity as a potentially time-varying, bounded coupling strength parameter. So really, the proof is just follows from theorem 1. Our PCO network with phase continuity meets all the conditions necessary. We're using a delay advance phase response function. All the oscillator values start within half the cycle. The key part is to look at what the effective coupling strength converges to. We just have to double check that it doesn't converge to 0, and we can find a subsequence of values that don't converge to 0. So that shows that the whole network will eventually synchronize. So that's the essence of how we're able to show that. In addition, we can talk about like how long it's going to take the network to synchronize under phase continuity. We can show that the time that it's going to take the network to synchronize is proportional to or inversely proportional to the average effective coupling strength, where that average effective coupling strength is just the average of all the potentially reduced in that time varying because of the phase continuity. Because our effective coupling strength is reduced because of the phase continuity, we expect that the time to synchronize is going to take a little bit longer, which should make sense. The adjustments aren't going to be as big because of the phase continuity parameters. It's going to take a little bit longer, but it's still going to be able to synchronize. So the proof for this theorem is really just a generalization of results by Wang and et al. So I won't go into the details of that necessarily. But since we now can show that the pulse-coupled oscillator network can synchronize under this sort of phase continuity, we can extend this to a robotic physical system where I want to achieve synchronization of the robotic headings. It really just follows again directly from theorem 2. We're using a delay advance phase response function. All the initial oscillator phase values are within a half a cycle because the robot headings are all within half a cycle. And we've shown already that the effective coupling strength won't converge to 0. So the oscillator phase values will synchronize, which means that the robot headings will also be able to synchronize. So that's synchronization. Before I show results, let's talk about desynchronization as well. For desynchronization, we're using a different phase response function that's shown in figure 4.2 there. But to help us analyze it, rather than looking at the phase response function itself, we'll actually look at the phase update, which is shown in figure 4.3. That shows what it kind of graphs what the new phase value is given what the previous phase value was. And what's important to note there is that the phase value or the phase update is monotonically increasing. It's always going up from left to right. So in blue, that shows what the standard original phase response function is. But because we have this phase continuity, because we have this rate constraint on the heading of the robot, on the value of the phase variable, this is going to result in a potential reduction in the adjustment that's going to be made. But it's going to still be monotonically increasing phase update. So the red line kind of illustrates that the phase update is still monotonically increasing. And so we can model this kind of phase continuity as, again, this sort of time varying coupling strength function for both the forward part where the oscillator is adjusting forward and the backward part where the oscillator is adjusting backwards. So to show that we're able to still achieve desynchronization, we'll take the same approach. We're going to look at a standard PCO network and look at what the behavior is when it makes instantaneous adjustments, but with this non-constant time-varying coupling strength function. So we have lemma 1 that shows we can do this. The details of it are a little tedious, but are really just generalizations of results by Gao and et al. So really it just requires that the phase update is strictly monotonically increasing. So it's always monotonically increasing regardless of even if it's time varying or not. Every time it's monotonically increasing, the network will be able to desynchronize. Additionally, we're only really concerned about what the coupling strength is at those pulse firings. So proposition 2 is very similar to what we had for synchronization. I really only care about what the coupling strength value is at those pulse firings. What it can be, whatever value it wants in between those times. So it's similar for the synchronization case. We just have to restate it for desynchronization. So with that lemma in place, we can then show that we can achieve desynchronization with our time varying phase response function. So long as the coupling strength functions and the phase update is still strictly increasing, which we can show using our phase continuity arguments. The phase update is always going to be monotonically increasing, so that means the network will always be able to desynchronize. Similarly, then we can extend that to show that the robot headings will be able to desynchronize under that sort of rate constraint of the robot heading adjustment. Again, the phase variables will be desynchronized, so the robot headings will desynchronize in a much similar way. So that's really just an extension of that. So with all the theorems out of the way, let's talk about actually implementing this. If we actually do some simulations with oscillator phase values and they follow this sort of phase continuity methods of the constant frequency method or the constant time method, are they still able to synchronize? So we set up a network of 6 oscillators that are all connected to each other, so an all-to-all topology. And we're able to see from figure 3.2 that the continuing arc does decrease all the way to 0. It's much slower than if they just instantaneously changed, as in if they just made that instantaneous jump in phase value, but they do still synchronize. So that's what we expect. The continuing arc decreases more slowly, but the network does eventually synchronize. But we gain the ability to adjust the phase values continuously rather than instantaneously. That's just for an all-to-all topology. If we adjust the topology so that each oscillator is only connected to its kind of 2 immediate neighbors, so we call this a ring topology. So not everyone is connected to everyone else. In this case, we still see the same idea. The network is still able to synchronize, but it is a little bit more slow than if it was making those adjustments instantaneously. So we see a similar process there. The phase values are able to change continuously, but the network is still able to synchronize. For the theorems, we consider only delay advanced phase response functions, but there are other synchronization algorithms that have been proposed. There's the original one by Peskin back in the 70s, but then there's been adjustments and modifications to those by Marulo-Strogatz, and then additional algorithms such as the reachback firefly algorithm by Werner Allen et al. All of these use a different method to determine what the phase adjustment should be, but the important thing to note is that none of them have an explicit coupling strength parameter, such as alpha. So the approach of analyzing a time-varying coupling strength parameter doesn't really work for these algorithms. Figure 310 shows what the kind of resulting phase response function would be for these algorithms. In each of these cases, the adjustment is always forward, rather than having some backwards and some forward. So our theorems aren't able to guarantee that these networks will be able to synchronize. But we thought, let's try it out. Let's look at what phase continuity does in these cases. And it turns out that we're still able to achieve a good level of synchronization. Still a little bit slower because the phase adjustments overall may be a little bit smaller, but overall the network is still able to synchronize to do it well. So we're not necessarily able to guarantee that other synchronization strategies will be able to synchronize under phase continuity, but we can still kind of illustrate that it does work fairly well. Even under different synchronization strategies, you can still use phase continuity to achieve synchronization. But not only did we do simulations, we also did some physical experiments with our robotic network. So we have a platform of iRobot Create 2, also known as Roombas. And these are really great to do experiments on because they have differential steering, so they're very easy to control. They have wheel encoder sensors, which allow us to measure how much the Roombas have rotated. For our Roombas, we limited the overall rotation rate to about 11 degrees per second, just to make things a little bit easy to program. But all of these are programmed using a Raspberry Pi 3 in Python. So we're able to write programs easily for that to control the Roombas. They all have RF communication modules that allow them to communicate between each other so we can send the pulses or the oscillators between each of the robots. They also have an inertial measurement unit or a magnetometer, a compass, that allows us to measure heading and orientation a little bit better as well. So with this platform, we can apply that robotic control algorithm to be able to control the robot's headings and see how well they're able to synchronize and desynchronize. So in the synchronization case, we have all 6 robots put together, so they're all communicating with each other in an all-to-all topology, and we can see that they are able to synchronize. The continuing arc decreases to 0. All the heading values of the robots all converge to the same value. So the robots were able to synchronize. So that's good. Additionally, outside of an all topology, if we just use a ring topology like before, where each robot is only communicating to 2 robots on either side of it, then we're still able to synchronize. It takes a little bit longer, but it does end up synchronizing in about the same rate as we saw in our simulations. So that's good. In addition to synchronization, we can also achieve desynchronization, so all the robot headings spread out, in which case then we use that desynchronization phase response function, where we have different coupling strength parameters that we use, and we're able to see that the robot headings are all able to desynchronize. They all spread out, and that desynchronization measure P does converge, go down to 0. However, one thing to note with the phase value or the heading values of the robot, that they all are slowly drifting backwards over time. And this has been noted because of the backwards coupling strength parameter. If you decrease the backwards coupling strength parameter, so if I decrease it all the way to 0, the robots aren't able to make any backwards adjustments. They're only able to make forward adjustments, but they're still able to desynchronize. And so we can show that similar behavior, but we don't get that sort of backwards drift over time. So we have our physical experiments of synchronizing and desynchronizing that we're able to achieve in a physical system. So that's great. Let me transition now to talking about some of those peculiarities of dealing with a physical system, particularly trying to figure out what an optimal phase response function would be. And I want to use that using reinforcement learning. But let me explain a little bit what are the limitations right now. Because with specifically for synchronization, there's several different limitations that we have to work around. First is that the initial continuing arc has to be less than half of a cycle, which is kind of limiting, because if you randomly initialize the oscillator phases, it's very unlikely that all of those initial random values will be within half of the cycle. It decreases, the probability of that happening decreases exponentially as you increase the number of oscillators. However, research has been shown to say, well, if you have a coupling strength parameter that's large enough, then you can overcome that obstacle. But because of our phase continuity, we know that that is modeled as a potential reduction or a potential decrease in the coupling strength parameter. So that means we're not necessarily able to guarantee that the coupling strength will always be greater than a half, which would ensure that we're able to synchronize from any initial computer. Additionally, all of the analytical results that are, or most of the analytical results that are shown, specifically the one for the phase response function that we were using assumes that we have ideal conditions. So the oscillators receive their pulses instantaneously, all the oscillator frequencies are the same, etc. But in real physical systems, you have a pulse propagation. So the oscillator has to send the pulse, and that has to propagate from one node to the next. Oscillators might not all have the exact same frequencies just because of hardware imprecision. And then you also have the added condition of a dynamic network topology, where the topology is changing over time, whether that's because pulses are sent but never received. You have nodes that are all moving relative to each other, so some kind of come into view and some go out of view. Also, if you just add or remove nodes to the network naturally, that's going to result in a dynamic topology. So all of these sort of non-ideal parameters make it really hard to figure out what is the best phase response function to have. Now, there have been results that have been looking into what is a best synchronization strategy, considering all of these non-ideal factors. For example, the Morello-Strogatz strategy from back in the 90s has been shown to almost be able to work basically everywhere, but it's very slow. It is better for modeling biological systems, but it is just very slow at being able to synchronize. Other results by Klingelmeyer et al. And Nishimura et al. Account for pulse delays. So when there's a known amount of delay in the pulses that are being sent, but they don't necessarily have a cooling strength parameter, and they require that the oscillator make a certain amount of adjustment regardless of where it is. And they don't necessarily have guarantees for certain types of topologies. So this sort of direct analysis by looking at the pulse-coupled oscillator network in these non-ideal environments becomes really difficult and potentially intractable as you start layering on more of these. So the approach that I wanted to take was, rather than me trying to figure out what the best response is, what if we have the oscillators figure out what the best response is? And we can do this using a reinforcement learning approach. So if you're familiar with how to train your dog or other animals to do a command you want it to do, you give it the command, does something, whether it does it right or wrong, you reward it based on, if it does it correctly, or you don't reward it if it doesn't do it. Eventually the dog figures out, here's what the best, here's what I'm supposed to do when they give the command. I'm supposed to sit, I'm supposed to, shake hands or whatever. I can do the same thing with oscillators. I can have the oscillators learn what is the phase adjustment they should make when they receive a pulse in the network based on the experience that they get. So they'll make an adjustment, and I can reward it based on how well they were able to synchronize. And over time, they'll be able to figure out what the best response is. What's nice about this kind of approach is that I can simulate all of those environmental factors. I can simulate all those non-ideal environment factors, and then look at how well does the oscillators change their behavior. Do they change their behavior? What effect does different environmental factors have on what the oscillators learn is the best response to take? So that's the idea. That's kind of the overall idea of using reinforcement learning in this way. Let me kind of overview what the overall framework is. So each oscillator has its state value, which is its phase value. They can all take an action, which is just the adjustment to their phase value when they receive a pulse. They all have their own oscillator frequency. What I'm going to do is I'm going to create a set of state action values. So this is a matrix of state action values, which allows the robot to kind of estimate how well a certain action is given a certain state. So for each state action pair, it can estimate how much reward am I expected to get when I take this action when I'm at the state. So using those state action values, each oscillator is going to choose a policy. That policy just tells it how is it going to respond at a certain state. Well, what action is it going to take? Basically, this is the phase response function. It's going to tell it how it's going to respond when it receives a pulse. So each of the oscillators choose their own policy. Those policies are then applied to the oscillators, and then we simulate the network for all the oscillators using those policies. At this point, we can pump in any environmental factors we want, whether that's a dynamic topology or different non-ideal factors such as non-identical frequencies or the pulse propagation delay. We can simulate that environment for the oscillators, and we can let the network simulate. After the network is finished simulating, we can then look at how well to reward each of the oscillators, and based on how well they were able to synchronize, what actions they took. We can use those reward values then to update state action values for each oscillator. In which case, in the process repeat, the oscillators use these updated state action values to choose new policy. That policy is then used to simulate the network again. We then determine a new set of rewards, which are then used to update the state action values, and so on. And over time, we're hoping that the state action values will converge to an optimal policy where the oscillator is able to synchronize most often. So that's the basic overview. For those of you who want all the technical details, I know there's a few of you out there. Each of the states the state is parameterized into p+1 different parameter values. And then our actions are then discretized into a+1 different action values. And so our state action value matrix is a p+1 by a+1 matrix. The policy that we choose for each iteration of that loop is using a Boltzmann distribution to determine what the policy should be for each oscillator. The reward for each oscillator is based off of how well it's able to synchronize. So what the change in the containing arc is. If it decreases, that's good. We want to give it a positive reward. If it increases, that's bad. We want to give it a negative reward. But we also penalize the oscillators for taking large actions. So we have an action penalty function, which penalizes it for taking excessive or large actions. We want to try to get synchronized taking the smallest actions possible. So as it simulates, we generate the sort of state action reward sequence of here's the state oscillator was in, here's the action it took at that point, and here's the reward that it got for taking that action at that state. I can use that state action reward sequence and update all of the state action values for each oscillator using those formulas. I won't go into all of them. There they are. It's just the SARSA algorithm, if you're familiar with that, but applied to the specific framework. So then for each episode, each cycle around the loop, we have the oscillators evolve or simulate for about 15 cycles. We then perform that back update of the state action values based on what the reward values were. We then repeat this 100,000 times, slowly decreasing the learning rate so that the state action values kind of approach their optimal values a little bit better. After all that's done, we can then choose the optimal policy, which is just the policy that says that best action to take is the one that gives me the largest state action value. So the optimal action will be the one that has the largest state action value for each of the state parameters, and I can use that to approximate what the optimal phase response function is. So with all that, what actually happens? So let's start out simple, looking at an ideal environment. So oscillator frequencies are all identical. The pulses are being sent instantaneously. And let's look at the simplest possible topology that we can have. That's two oscillators that are both connected to each other. What we get is basically our standard delay advanced phase response function, which should be what we expect. This matches our analytical results that we would get. That's shown by Wang et al. But the reason we get this is because the containing arc for two oscillators is always less than half of a cycle. So the conditions are met for having that standard delay advanced function. So this is what we expect to get. So that's good that our results are at least consistent with that. So what if we expand that back to our 6 oscillator network, where we have 6 oscillators that are all connected to each other? When we run the reinforcement learning algorithm, we see that we don't get that normal delay advanced function. Instead, we get this sort of hybrid stuff where initially and at the end, it's following that sort of standard delay advance. But in the middle, you get this response that's different, where instead of doing the maximum amount of change, the oscillators learn that it should take some amount that's proportional to how far away it is from the end of the cycle. So really, this is combining strategies by Wang et al., that standard delay advanced function, with strategy is Merlo-Strogatz, where you make an adjustment proportional to how far you are into the cycle. So I can model this using a sort of piecewise linear model that's shown there in figure or in equation 511. The model is shown in the pink value and figure 5.2. But the reason we get this is because 4-6 oscillators were not necessarily ensuring that the containing arc is always less than half the cycle. Because the policies are chosen randomly, the oscillators will make adjustments that move them outside of half of a cycle, in which case then the previous analytical results don't necessarily apply. So this is kind of expected that we don't get the exact response, but we get this different behavior. With additional experiments, we really are able to determine that the topology is really key in knowing what the actual learned response will be. So for example, for 6 oscillators in a ring topology, so each oscillator is only connected to 2 other oscillators, you get a similar response than if you had 3 oscillators that were all connected to each other. Both of these have an in degree of 2. All the oscillators have the same in degree in this case, and you see that we get a very similar learned phase response in both cases. So this leads us to really see that the in degree of the oscillator is important to knowing here's what the reinforcement learning strategy is going to have the oscillators learn over time. So with that in mind, we then simulated a whole bunch of networks, different random networks where also the amount of connections varies, and we plotted and modeled our model fit for what the phase response function is, and plotted out here's what those parameters C1 and C2 are, what the boundaries are, where it changes between that standard delay advance function and that sort of proportional phase adjustment quantity. And so we model what those are, and we simulated for various different sizes of network. And we're able to see that what is learned is actually very predictable. You can kind of model an exponential curve to those function parameters based on what the oscillator in degree is. So the oscillator, so when the oscillator in degree is 1, that means there's only one other oscillator that it's receiving pulses from. Then it kind of models that sort of direct delay advance phase response function. But as you increase the oscillator in degree, the parameter C1 basically decreases to about 10% of the cycle. So only during that first 10% of the cycle will it do the delay advance. And then as the oscillator in degree increases, the advanced portion is only going to happen during the last 25% of the cycle. Everywhere else in between is going to be that proportional adjustment range. So this is what we are able to see under ideal conditions. So we then say, well, what about non-ideal conditions? What if we throw at it non-ideal oscillator frequencies or pulse propagation delays? And when we have frequency variations of varying amounts, we end up getting very similar results from our reinforcement learning. Basically, they are exactly the same as they were in the ideal case, where the frequency was the same for all the oscillators, even as you increase the frequency variation. So this leads us to conclude that the optimal response is almost exactly the same as in the ideal case. Even with propagation delays, you see that the phase response function is still more or less the same of what is learned, even as the amount of delay is large, and even if it's random over time, you still get a very similar behavior response. If you combine frequency variation and the pulse propagation delay, you get the exact same learned phase response function back out. So this leads us to conclude that our response in a non-ideal environment is going to be exactly the same as it was in the ideal environment. And this kind of makes sense in the sense that for our reinforcement learning framework, the oscillators are not given any information about what is going on in the network. They're not given information of, oh, there's this amount of frequency variation in our oscillators, or I'm expecting there to be this amount of propagation delay. The oscillators are not given that information, so it's seems reasonable that they would make the assumption that, oh, I'm assuming an ideal environment and something the same sort of adjustment in that way. So our conclusion is that the optimal phase response function in non-ideal conditions, in non-ideal environments, is the exact same as it was in the ideal environment. So we can use that same sort of learned parameters for our phase response function model to be able to simulate behavior. So when we compare our new phase response function that we've learned to other standard synchronization algorithms, we see that we do get this sort of improvement in being able to synchronize the network. So for example, here I've got 9 oscillators in this sort of star topology. You've got 8 oscillators that are all connected to a single central oscillator. And we're able to see that as you increase the coupling strength, the amount of time it takes to synchronize decreases, and it matches very closely with other synchronization algorithms. But you're able to synchronize much more frequently. The probability of synchronization is much higher. As the coupling strength increases to 1 in this case, we see that the Murillo-Strogatz algorithm is able to synchronize a little bit more often, but the time that it takes to synchronize is orders of magnitude larger. So we kind of see that this learned phase response function is kind of doing a trade-off between Murillo-Strogatz and kind of that Wang et al. Standard delay advanced phase response function. But in our non-ideal cases, we see the exact same behavior with 6 oscillators and an all topology where we have some non-ideal parameters thrown at it. We're able to see that as the coupling strength decreases, the learned phase response function is able to synchronize much more often and to a greater degree for over a wider range of coupling strength values. Even when we increase the non-idealness, the variation in the frequency and the time delay, we're still able to see that our learned phase response function is able to synchronize more often as the coupling strength decreases. And I'm just going to show a whole bunch more simulation results here. Here I've got 8 oscillators in a ring topology with some non-ideal parameters. Again, we're able to see that our learned phase response function is able to do better than many of the other synchronization strategies. In this case, we see that the Murillo-Strogatz algorithm is able to synchronize more often in that sort of middle range of coupling strength values. But what is not shown is that the time that it takes for the network to synchronize is much larger. But even with that, as the coupling strength decreases much more slowly, then our learned phase response function is able to synchronize more often. For 11 oscillators in this sort of near 4 topology, so rather than each oscillator connected to its 2 nearest neighbors, connected to its 4 nearest neighbors, we're still able to see that our learned phase response function is able to synchronize more often than any of the other strategies. We even throw at it a random topology where the number of the connections between oscillators are randomized, and we're still able to see that our learned phase response function is able to synchronize more often, even in non-ideal cases. So with that, we will finally conclude. Regarding our phase continuity algorithms, that we are able to show that our PCO networks, our pulse-coupled oscillator networks, can synchronize and desynchronize under phase continuity. And behavior can be described using a sort of effectively reduced time-varying network coupling strength. The phase continuity methods even work well in synchronization strategies that don't necessarily explicitly include some sort of coupling strength parameter. Some additional ideas that could be considered regarding phase continuity is looking at various different desynchronization and synchronization algorithms and what behaviors you get when you see phase continuity, as well as analyzing the effects of those non-ideal factors directly under phase continuity. That might be interesting to look at as well. But there are also additional phase continuity methods that you can consider. We just considered 2, but what if we, instead of having the frequency adjust at a constant value, what if we had the phase value have a smooth acceleration? Or what if we considered cumulative effects of multiple pulses all at once? Those are different things that we could try to consider going forward. Regarding an optimal response using reinforcement learning, we were able to find a new family of phase response functions where the response is based on whatever the in degree of the oscillator is. We don't have to necessarily redo all the reinforcement learning again. We can instead model, here's what the function parameters should be in order to achieve the best response. These new phase response function family is able to synchronize better than any of the previous analytical solutions we saw in both ideal and non-ideal environments. Some future work that we can consider in this case is that we can look at how we could achieve different designs in the reinforcement learning framework, whether that's with the reward value and how we calculate that, or just the overall structure of how we're implementing the reinforcement learning. Lots of different reinforcement learning strategies have been proposed, so applying those in this case may give slightly different optimal responses, which would be interesting to consider. In our case, we also only consider phase adjustment values, phase adjustment functions, but potentially it could be useful to look at learning what an optimal frequency adjustment would be, so that in non-ideal cases, the oscillators would be able to synchronize their frequencies as well. And while we only look at synchronization algorithms with regards to reinforcement learning, it could be interesting to determine what an optimal response for desynchronizing oscillators would be using the same techniques. With that, I will conclude by acknowledging that a lot of my research has been funded by various National Science Foundation grants, but I would also like to give some special thanks to some people, specifically my graduate advisor and committee chair, Dr. Yongqiang Wang. He's the one who introduced me to the ideas of pulse-coupled oscillators. So I'm appreciative of the guidance that he has provided for me in my time here at Clemson and for my research. I want to thank my committee members, Dr. Richard Groff, Dr. Ian Walker, and Dr. Umesh Vaidya, for taking the time to be able to listen and to help me with the presentations of this, as well as kind of overseeing, taking the time to look at my research to help me improve in that way. I also want to thank the undergraduate students from the Robotic Networks Creative Inquiry. They're the ones who helped to develop that robotic platform with the Goombas. And so I appreciate the time that they were able to take over various years, helping to improve and make sure that all of those processes work together smoothly. I do want to thank my parents, Stephen and Patricia Angel. They don't always understand exactly what it is that I do, but they've always been very supportive, and I'm glad to have them help me through this time here I have at Clemson. I also want to thank the various people who have reviewed or edited portions or parts of the research papers that have led up to this dissertation. Thank you so much for helping to improve grammatical errors and pointing out other various improvements that can be made over time. With that, I will conclude and will be glad to answer any potential questions that you all have. Thank you.